Hello everyone, I'm Zhelin. It's my pleasure to introduce our paper titled Hierarchical Co-Maintenance on Large Dynamic Graphs. The authors are from East China Normal University, Guangzhou University, and the University of New South Wales. KCO is one of the most well-studied models for mining cohesive subgraph. It is defined as the maximal connected subgraph, where each vertex in a subgraph has at least k neighbors. According to the definition of KCO, we can get two properties. The first one is containment, that each k-core is contained by a k-1 core. For example, in this graph, we can find that each 5 core is contained by a 4 core. And the second one is disjointness. It means that any two different k-cores are disjoint. For example, there is no overlap between any 4 cores or 5 cores. According to the two properties, the k-core hierarchy can be represented as a tree. The subtree rooted at each tree node at layer k represents a k-core and has the same vertices as it. For example, the subtree rooted at this node represents a 4 core on graph G. The tree edge of two nodes represents that the k-core associated with the child node is contained by its parent node. For example, the 5 core of the node marked by green rectangle is contained by the 4 core marked blue. The k-core hierarchy can be used for cohesive subgraph detection, study user engagement, and graph visualization. In the detection of cohesive subgraphs, a recent work computes the k-core with the largest density in the hierarchy of core decomposition. For the user engagement study, it is validated that the engagement of a vertex is usually in a positive correlation with its coordinates. However, our experiment results find that the engagement evaluation of a vertex can be more accurate by considering both its coordinates and its position. Besides, hierarchy k-core is a natural representation of the graph decomposition. Generally speaking, a large graph can always decompose into a tree with a small size. As real-world graphs are often highly dynamic, we studied the problem to maintain k-core hierarchy. So we gave the problem definition. Given a graph, its k-core hierarchy and the edge set inserting into or removing from the graph. Our task is to update the k-core hierarchy. To our best knowledge, there are two kinds of existing works. The first one is the algorithms for maintaining coordinates after graph updated. And the second one is to construct and update the k-core hierarchy. However, existing studies cannot efficiently process the update of k-core hierarchy. So we propose two methods for the two situations, inserting edges and removing edges. We first introduce the approach for the inserting case. After the insertion of the edge, we use the algorithm for co-maintenance to update the coordinates of all vertices. According to the existing study, the vertices whose coordinates changed have the same coordinates, and their coordinates increased by 1. After updating coordinates, we introduce how to update the structure of the tree. The overall solution is to move each vertex to the correct layer and then update the tree layer by layer depending on the two properties. We discussed each k-core in different k. For the k-cores where there are coordinates larger than k+1, the k-core keeps the same after the insertion. For the k-cores whose coordinates not bigger than k, the inserting edge will connect some k-cores. Besides, the vertices whose coordinates changed will connect some k+1 cores. According to the above analysis, we can update the structure in 3 steps. The first step is to link two components for any k not larger than k. For example, as shown in red rectangle, we merge two subtrees into one. The second step is to update the vertices with changed coordinates. For example, we locate the node of V5 whose coordinates changed, create a child node of it, and move V5 to the child node. And the last step is to link some components on k+1 core as the coordinates of some vertices increased to k+1. For example, the 3 edges linked by V5 connect the 3 cores, as V5 is new to 3 core. We locate the tree nodes which represent the 3 core and merge them into one. So far, we have completed the maintenance for one edge insertion. To extend the solution for inserting multiple edges, we can see that both step 1 and step 3 are to link components, and step 2 is to move vertices. So the solution for inserting multiple edges is to update all vertices corners and link all components that need to update at the same time. To link the components at the same time, we use a candidate set to store the node pairs that need to be adjusted. At first, we put the node pairs linked by inserted edges, or each vertex whose corners has changed. After initializing the candidate set, we adjust the pairs of C layer by layer in a bottom-up manner. When we deal with the node pair at the same layer, for example, the pair marked by a red arrow, the two nodes should merge as they will be in the same K-core. And for the node pair at different layers, the vertices in two blue nodes are connected pass through these red vertices. We should merge them, so we create a new pair of them and put the pair into the candidate set C. And they will be merged when we adjust the node pair with smaller corners. Next, we briefly introduce how to maintain the tree after removing edges, as it is the reverse process of insertion. Different from insertion, the main operation of the removal process is to split nodes. The solution is to call split node to adjust the tree nodes that may split. Split node is a function to check and split the subtree routed at the input tree node. Here is an example of split node. We can see that the focal split into 3 parts after removing edge V2, V17. We traverse all vertices in the input nodes and link their neighbors on tree. Finally, we reconstruct the subtree depending on these linkages and finish the process of splitting the focal. The solution for removing multiple edges can be extended from the above works easily. We use a candidate set to collect all tree nodes that should be visited by split node. We call split node for each node in the candidate set in the order from large corners to small. If the node splits into over one pass, we will put its parent node into the candidate set C. The processing will continue until we have visited all nodes in the candidate set. Here are our experiment results. We did 4 experiments on 10 datasets up to billion scale to prove the effectiveness and efficiency of our algorithms. As mentioned before, it is a better way to consider both corners and its position in the hierarchy to estimate the engagement of users. To prove it, we investigate the engagement of the authors and the characteristics in the K-core hierarchy. The dataset is picked as the co-author graph from DBLP in 2019 and 2020. The engagement of each user is defined by the number of published papers. We compute the percentage of the users which is in a node with high activity than its parent node, denoted by TH, and compute the percentage of the users which is in a subtree with lower activity than the largest K-core. We can see that most of them are close to 100%. Recently, an approximate solution is proposed by extracting a K-core to find the densest subgraph. The baseline solution for dynamic graph is which first update the tree and then compute the largest density subgraph. In this experiment, we apply our algorithms to the solution, which is to update the tree by our incremental algorithms, and then recompute the largest density subgraph on the changed node. We can see that the runtime is smaller than the baseline by up to 3 orders of magnitude. To prove the efficiency of our algorithms, we compare our algorithm to the 2 baselines, where LCPS plus is to reconstruct the tree after updating corners by the incremental algorithms. We can see that our 2 algorithms are faster than the baselines on most datasets, especially for large data. These 2 figures report the trend of the 2 algorithms with different x values. To make them clearly, we pick up 3 datasets of them. In these 2 figures, the polylines with markers show the running time of the batch incremental algorithms, while the others are the simulation time if we call the single algorithm x times. We can see that for the 2 removal algorithms, our batch algorithm has a scant effect when the x grows. However, the batch algorithm for insertion works well as both the running time and its growth rate are significantly lower than the single algorithm. That's all. Thanks for your listening. Is there any questions?